Uh, Good afternoon. I know that I'm standing in between you and the tea break, so I will do my best to complete it in the given time. I mean, for a small change, okay, we have seen a lot of thermal catalysis so far. I mean, you see now I'm choosing a topic which is basically on water splitting, which is actually a reaction which is there for at least like close to 5 decades or even more. If we try to, for the information of our guests, okay, so I'm representing Indian Institute of Technology, Hyderabad, which is on the other side of the city. Maybe I don't know their bandwidth. I request you to please make a visit to our campus. Okay, so this is one of the buildings of our place, our campus. As I mentioned, we are referring to a reaction which is as simple as it appears, like, okay, just you need to have some amount of energy, okay, which is very much sufficient in the form of the solar light. And you need to have a semiconductor, okay, that's all we need, okay, so you can have a photocatalytic reaction where it's a single part reaction, or you can also have two electrode system where you can separate two half cells, okay, so that's how you can produce hydrogen and oxygen. I'm sure that everyone of you probably are aware that this reaction demands some amount of energy because heat of formation of water or water formation is an exothermic reaction. Naturally, you need to supply certain amount of energy. And if you try to look at, okay, so the thermodynamic potential that is needed typically is only 1.23 volt. That means other than silicon-based semiconductor, many semiconductors are more or less any colored substance, okay, which is more or less like a semiconductor, has the capacity to split water into hydrogen and oxygen. But the problem here is that, okay, this reaction, even after 5 decades, okay, so this is not actually a practical reaction for the known reasons. As I mentioned here, you just need to have just 1.23 volt, and the band edges should be separated by valency band, and the conduction band should be separated by minimum 1.23 electron volt. Of course, there is a strong pH dependence on this reaction. More or less people report, okay, so close to 20% efficiencies, but they are either done under whole scavengers, okay, so under alkaline conditions, okay, so but not many reports we can find, because when the efficiencies are not really great, the student also doesn't want to do under neutral conditions. That's one problem also here. So pH has a strong influence, and you see clearly that, okay, so in any case, the potential difference is basically like 1.23 volt. For every pH shift, okay, we are making 55 millivolt difference. And thanks to the semiconductor understanding, now there are several opportunities we have, especially with the help of heterojunctions or nano, various combinations. Now you can think of many semiconductors that can do this job. To make it very simple, I think you need to have an N-type semiconductor for the oxidation reaction. You need to have a P-type semiconductor for the hydrogen evolution reaction. More or less, both reactions have its own ways of improving the reactivity. Each material has its own way of doing it. But at the end of the story, if you look at, you make a heterojunction, as simple as if you try to look at photocatalytic, it's easier for me, because just like, okay, I take, an RB flask and I try to put a catalyst where I see gaseous evolution. Of course, one problem is here that both gases are mixed, okay, you don't separate them. But the second aspect of it is that the reaction is limited only by the surface reactivity, because photocatalyst is also a surface reaction. If you really want to separate them, I think you need to have a junction has to be formed. Okay, so you're making two half cells. There comes the complexity, because you have an electrode, anode, and you have a cathode, or you have working electrode, you have counter electrode. In between, you have the electrolyte. So now the story goes more complicated. How will you choose the combinations? Okay, is it like a simple heterojunction I can form, or is it like a G scheme I'm looking at, or is it like a scheme I'm looking at? So what not? All the permutations between A to G, we can think of it. So a simple way to understand is when you try to combine these two in a say for example in a dual electrode system, you need to have the band bending happening. Otherwise, there will not be at equilibrium. You will not see that. Okay, so there will be some kind of work functions which are matching. So under those conditions, you see an N-type semiconductor. Okay, so there should be a band bending in the upward direction, and say for example a P-type, there should be this one. So the complexity comes, okay, with respect to the reaction taking place here. The reaction taking place here, the charge has to be transferred through the external circuit, or in other words, when you close it, okay, so that's where the charge transfer has to go. And from there, once again, like how the electrons are transferred now to the p-type material, so the charge transfer resistance also plays a role. So now this reaction is known for many decades. Okay, so now what are the possible scenarios which now people are, at least like last decade, okay, thanks to the momentum towards the green hydrogen, I think, though this is not a commercial reaction as on today, but I think thanks to that, okay, so now there are ways to improve the efficiency. This is like charge transfer efficiency. Okay, so then you can play with the electrodes. You can also play with a simple combination like metals can be doped. Okay, so then you can also look at co-catalyst. This is very much needed for hydrogen evolution. Or if you try to look at known heterojunctions, and thanks to the natural photosynthesis, which you can always look at the heterojunction formation. That means that it's not a difficult thing to choose a semiconductor. It's much more difficult to prevent the recombination. It can be a solar cell, or it can be even a PEC water splitting. The whole idea is like, how would you prevent the recombination? So the recent, we are all aware that, okay, both the Nobel Prizes in chemistry at one point of time, or at least like last year Nobel Prize was on semiconductors, so this is on ML basically. So the plasmonic metals, okay, based systems have, in other words, the semiconductor, as I said, it's not a difficult part for me, but when you try to decorate your semiconductors, it can be any semiconductor, when you try to decorate with a quantum dot or even plasmonic nanoparticle, you can feel some additional, or you can realize some additional advantages. That's what I'm actually trying to do. So this is what the literature essentially says, that you can have type 1, type 2, or even a PN junction, which is known, especially this is where the backbone of photovoltaics. And you can also think of a metal doping or metal loading. Okay, so then you can think of a G scheme with and without a mediator. So these things are reported very well in the literature. But if I'm actually going to talk about this kind of a thing, very specific to these things. It can be a noble versus non-noble metal. The one way you can think of it is that, okay, when you try to decorate, okay, so a metal or a quantum dot, okay, say on a semiconductor, so the additional thing which comes into the complexity is like your Schottky barrier. Because this is a semiconductor, on top of it you are putting metal, so the Schottky barrier is something. So that means the story appears simple, but it goes little complicated time to time. But until one point of time, we know that there is only a way of making a spherical nanoparticle, because the surface free energy of the sphere is much lower compared to rest of the configurations. But if you practically think of it as on today, if you really want to tap the energy, say for example, sunlight has a variation all the way from the small amount of UV all the way it goes to NIR radiation. If you try to look at the cutoff of it, nearly 50+% is towards the NIR region. Okay, so that means you have 46% in the visible and okay 3 to 4% UV, but rest of it typically goes unutilized, because your material cannot utilize, or the semiconductor, whatever you can think of, more or less there is a cutoff with respect to 1010 whatever silicon, which is 1.1 electron volt. Now there are ways, now this is a known literature, okay, so there are ways in which now you can try to modify the morphology. You can play with it in a way. When you try to play with this kind of morphology, if you look at like, okay, you're in a position to go more, there is a way now to improve the light absorption cross section. That's one thing. And the moment you absorb, you try to facilitate more light absorption, then the additive effects can be, it can be basically a dipole effect, or it can be quadrupole effect, or it can be hot electron injection. So there are multiple events which you can think of. That's where the small nanoparticles come into the picture. If you try to decorate plasmonic nanoparticle, argument's sake, when it is excited with a suitable wavelength, okay, or radiation, there are two effects to it which can be which can be utilized for the PEC water splitting. The first part of it is the excited, due to the surface plasma resonance for the known metallic particles, light absorption cross-section increases, you have more light that is absorbed, as a result of which now the excited particle has two options now. Through a radiative decay, it can release its energy, or even it can create additional electron hole combinations. Okay, so that way, whatever be the combination you can think of, the plasmonic enhancement can be extrapolated or can be utilized either by increasing the light trapping or even the cross section. That depends on small versus big particle. Whereas you can look at that if the particle size is suitable enough, you can think of hot electron injection, or you can also it can also lead to the plasma induced resonance energy transfer, which is like a PET kind of a thing. So this is actually, you look at that, the same gold is especially like noble metal based. Okay, so the small particles are like the quantum dots or plasmonic nanoparticles are well studied. If you look at here, the light absorption cross section is basically, or in the sense like the lambda max is basically pushed all the way from, say for example, with increasing size of it, you see there is a redshift which is happening. So this is where like now you see that the absorption cross section also increases. In a way, you can tap now more energy which is otherwise not utilized, because many a time we take actually a semiconductor argument say TiO2, so then you try to modify the TiO2 band gap, but essentially if you bring all the way from 3.2 only to around 2.9, that means that the rest of the energy which you have goes unutilized. So the whole idea of it is like, based on the earlier effects, how would you increase now the light absorption cross section, or in other words light absorption. So that's where you can think of it like you see more amount of light can be practically used for these scenarios. The additional effect which you can think of is that the hot electron injection, because as I said that there is a barrier which is inbuilt, because when you put actually a metallic object on a semiconductor, there is a barrier, otherwise like the electron flow cannot happen. So for that, okay, you need to have some kind of actually a small particle which is highly energetic. The way you look at in this case, okay, so if the particle is so small, so that means it has a possibility, especially for this. In the case of gold, I think you need to have the size of at least like less than 20 nanometers. So this way. So, but if you look at in this, these are many things which are known, okay, in the literature for some time. But if you try to look at most of the noble metal combinations are, most of the combinations of plasmonic effects are mainly limited to gold and silver kind of combinations, but non-noble metal and noble metal. So there is a way in which you can play with it. If you try to look at more or less like if you try to look at the visible light, okay, or the solar spectrum, as I mentioned that, okay, you have very much of the radiation which is towards NIR region. So that means then I told, at one point I told the students that there are many studies which are concentrating on, say for example, visible part of it. But if you try to look at like say the cutoff region which you have, that's where like the bismuth sulfide, say for example, kind of rods which he has prepared. And if you try to see that, okay, the absorption happens in the edge of it, like the visible and NIR region. And okay, so then this material has a favorable conduction band edge position for the hydrogen evolution to happen. And now on this, you can try to decorate, which is a noble metal nanoparticle. So if you try to see this one, then the suitably you can construct the band edge, okay, so the diagram by using the combinations of cyclic voltammetry and say the UV visible. Then you can actually think that the simple way you can make a catalyst is, or the electrode is like we make one square centimeter. So you can use either Dr. Blade technique or spin coater, whichever way you can think you can make it. Now you can beautifully decorate these nanoparticles. So far these are spherical nanoparticles. If you try to decorate them, and you can actually see that mostly if you look at bismuth based materials, which are also known for thermoelectric materials, because of the nature of these materials, they can also be active under dark. Okay, so if you look at, they are not very active under dark. Then the moment you shine the light, okay, you look at like the current density improves. And you can also at the cathode side, okay, you can, or counter electrode side, you can estimate now the hydrogen which is evolved. So the way in which was you look at that, I am only talking about a cutoff region of 1.5 electron volt, okay, so which is nearly the cutoff. On that, if you try to put, okay, so the small gold particle, okay, which you decorated, has a significant influence in terms of giving more amount of hydrogen. So as I mentioned that many a time people talk about, okay, the efficiencies of close to 20%, but I think as I mentioned that you have a sacrificial thing in those conditions. Now the way the suitable energy levels you try to construct it, okay, it works. Then you can actually try to think about that, okay, so like this is the optical study, and you have the X-ray study, and you can actually look at like the way the rod has grown. On that you have a tiny particle which is roughly around 15 to 20 nanometers you have. So this is where you can decorate it. So that means like you can confirm each one, and okay, so then you can look at like the efficiency somewhere, and you can as you see that it's going to happen. and the conversion efficiency typically goes around, say for example, up to 4 to 5 kind of a thing. But so far, as I mentioned, that this was once again a noble metal based. Okay, so if you really want to look for non-noble combinations, okay, so then we look for some other. Okay, finally we went to bismuth, which I will also tell you. So you have this bismuth vanadate is known is a material which is inferior, which cannot liberate hydrogen. This can only act as actually working electrode. So this cannot do hydrogen evolution reaction. So that means what you are looking at basically is the current due to the oxidation part of it. It also has a smaller band gap of 2.4, and you can actually try to dope, okay, so molybdenum it's because this gives also a little more stability to it. So this is where you can actually think about, and this where the final stage of the catalyst is going to be. One good part of it is that it is relatively stable. If you try to look at like it is stable, there is no degradation, at least like there is no efficiency loss that was observed. And the hydrogen generation is also reasonable, and the mod Schottky basically confirms that, because you need to have as I mentioned, that final as I said, this is basically an N-type material. If you really want to confirm, you have to do. And the most important thing, the moment you try to put some kind of a doping, and you look at these are individual combinations, the moment you try to put the resistance, what was offered by these materials has actually significantly come down. And now you see that the RCT value, or the charge transfer resistance, is very small. So, but as I mentioned, the title says that it's a non-noble metal. So then actually the idea here is that to use like a bismuth nanoparticles as photoanodes. So in this case, once again, we have the same combination. We didn't change it. The same C3N4, we didn't change it. But instead of gold, now we try to go for bismuth based nanoparticles. Okay, so these are the small things which we are decorating it. Now this is how you can construct the energy level diagram, and you look at that. Now mostly the SPR effects are known either for gold or either for silver or mostly for copper, this kind of non-noble metal. It's not that I was the first one to, or we were the first one to report. They are known, but it's less explored compared to other features of it. One beautiful part of it is that you can tune this gap in such way, or you can actually try to tune the size of it. That way you can make it suitable for this one. You look at that, no, these are small band gap semiconductors. The recombination is a more dominant one. In a way, if you really want to prevent this recombination or to minimize this recombination, the way you need to have, there should be a relay of it, like there should be a stepwise transfer of the electron. So for that, okay, so the moment you try to decorate this one, okay, so of course you see that, no, so say for example, this is how the preparation can be made. It's a simple chemical reduction based on this. Okay, we took this one and did chemical reduction, and you just sonicate it and you try to do Dr. Blade, and finally you end up with the electrode of your choice. And you look at that, no, the current improvement is considerable. Okay, so C3N4, though many times you see good reports about C3N4, especially in these conditions, it's actually current is in milliamps. So then you look at like this one, and the moment you try to put bismuth based nanoparticles, okay, so your currents are improved, and okay, so the STH conversion, whatever, solar to hydrogen conversion. I think many of you are aware that if you really want to have this reaction, okay, as a benchmark reaction, the STH value should be closer to 10. That's where this like a holy grail. People think that simple water splitting by using solar light will be practical if STH is nearly around 10 under neutral conditions. So that's where basically you look at here. Okay, so the known combination which you can look at. The same thing you can also play with other combinations. Instead of bismuth nanoparticle, you try to do the same. You try to do the same thing on, say, for example, RG and RGO instead of like C3 and 4. You can also see some kind of an effect. But I think once again, all these things boil down to one good part of it is that they're stable. Okay, they give continuous hydrogen evolution, and also you look at that IPC values. Okay, so are also reasonable, and you can also look at that the way you try to modify it, your RCT value is going to go down. So then actually this is okay, once again another study based on the same thing whatever I've shown previously, this one. But so far I was only referring to a working electrode, which is basically known because many oxides which are known to do oxygen evolution. Okay, so these are known. But a little more sluggish part of it is towards the hydrogen evolution reaction. For that you need to have a P-type combination. Somehow if you scan the literature, the best catalyst comes with respect to copper. Okay, so though other combinations are well known, somehow like Cu2O, CuO, this kind of combinations, okay, so +1 +2 copper based combinations are the ones which are best p-type combinations you can think of. But one way you can actually think of it is that, okay, so can we make this plasmonic copper based particles on, say for example, okay, this kind of a combination, this like a working electrode, then you can have some kind of a p-n junction kind of a combination. So this kind of a junction you can try to look at. So in this case, okay, so you try to look at this copper is basically decorated the way it is like. So then you look at the combinations you have. So that means copper based nanoparticles in this case. Okay, so that means you try to put an SPR effect. Okay, so then you can actually feel it. But if you scan, as I mentioned, if you scan the literature, the p-type candidates which are like CZTS, these are some kind of, you see the drastic, as I mentioned, most of the reports were basically on a working electrode. If you try to look at a significant improvements were reported when actually a p-type combination like CZTS, when this was actually loaded with this kind of platinum kind of combinations. So the CD substitution, this is a reported literature. Okay, if you look at cadmium substitution, it improves the significant activity of the photocathode. This is mainly because, okay, so the band edges and say for example this is tailoring, and cadmium substitution lowers the the valency band maximum, and you look at that, okay, at neutral, highly, say for example at 0 volt, which is the theoretical potential for hydrogen evolution. That means you practically look at that huge currents which are reported under these conditions. So taking clue from this, okay, so but we realize that, okay, so having copper, we all know that the reduction potential of copper is only 0.34. It's much easier to oxidize copper. And you look at that copper water bottles which you get, if you leave it for half an hour, you start seeing the oxide formation. It's not as stable as your gold. Okay, so that means that there is a way you should prevent the oxidation of copper. So then what we took in this case was, in our study, the student has done in a way like the copper oxide, which is a known kind of a p-type material. So the Cu2, I cannot say Cu2s because this is a non-stoichiometric kind of a thing, but at least like sulfide, okay, so the ones we try to reduce it with an organic linker, okay, so that like say for example oleic acid and this kind of combinations we have used. And if you try to just heat it and you try to reduce it, okay, so because you have some kind of a sulfur which is present there, so that it's reducing it, converting to sulfide. So this one we try to use it in combination with the copper oxide and copper sulfide. So that combination you can actually see the beautiful dispersion happening in this case. So this is where, okay, so you can actually try to play with this combination for this p-type material. You can see that, okay, so that means it has a good absorption in the visible region. And say for example, okay, so you can also look at that, okay, the excited lifetime is relatively longer. So then you can also look at that it has a good absorbance, and especially in this region I'm referring to, because the previous cases you only concentrated on these regions, but now you look at once you have made some kind of a rod kind of a thing, so the NIR starts active for this catalyst, and that's where you start seeing that, okay, this is active in this case. So that's the combination which we looked at. And all other studies, like as I mentioned that I'm not a fan for doing these things under highly alkaline conditions, okay, so because this is not very practical. Many a time you report good efficiencies, but you come back with a question, or you get a question that, okay, you have a whole scavenger which is actually playing into it. So then you look at that, okay, this is under neutral conditions, okay, you look at all the combinations you can think of, you try to vary now the loading of, say for example, okay, so the nano rods kind of a disk kind of a thing. Then the way you're seen in the earlier cases, okay, so it goes on, the activity is going to be improved, and at one point, okay, so you see that no, this is an optimized one, it shows good activity and you have very good currents, and okay, so this also like, okay, so it works well over a period of time. That means the difference is like, okay, if you try to look at the combination, you get say for example good currents, okay, say for under these conditions, and these improvements are significant when you compare with only copper oxide based, which is what known in the literature. Copper oxide combination, as I mentioned, copper +2 or copper +1, these are the good combinations of p-type materials. So we are trying to strengthen this combination, okay. So the moment you go from, say for example, neutral to basic medium, of course you see that the currents are going to be more, and okay, so then the efficiencies are also going to be normally reasonable. Then you look at, you try to give one question comes in all of us, our mind is like, do we really need, okay, copper oxide copper sulfide combination? If you just look at the catalyst is, as I mentioned, the electrode is not stable, which is a known thing. As I mentioned, copper oxide works okay at one particular time, thereafter it degrades. Now you look at that over a period of time, of course this is also decaying. Now you see that this is actually, this degraded, okay, at least like in 3 hours, I think 100% decay. But whereas when you try to look at in this case, okay, so there is some, at least like some percentage of activity it remained. And you can also give the hydrogen evolution comparison. Okay, this is where you have, and okay, you look at, okay, say for example, the other studies which also confirms that, okay, the Faraday efficiency, if you report, all these things look to be good. So then if you try to look at the RCT value, like just look at charge transfer resistance, it actually tells that, okay, so that means you need to have some kind of a sulfide combination, because this may be selectively, we were also thinking like what made now copper oxide more active in the presence of copper sulfide. That means this can be possibly due to some kind of a selective poisoning effect. So then, I mean, like if you really want to look at, I mean, like say, as I mentioned that this has an absorption in the NIR region. And if you try to look at, okay, say for example, it clearly tells that, okay, so the catalyst is active, okay, so or the electrode is active basically under, and air absorption leads to increased surface temperature. That's where probably like, okay, so the in situ you also have a little bit of temperature built on this one. And you look at that, the current nearly remains, okay, the same, at least in all these cases. The photocurrent enhancement is also seen slightly at higher temperatures. So then this was also with the help of my colleague. Okay, I'm not an expert in this DFT these calculations. With the help of my colleague, actually we tried to confirm that, okay, so the DFT studies revealed that, okay, so the surface active sites are going to be more and more, okay, so especially when you have the sulfide combination, that's where like, okay, you are going to favor this. This is also aiding because you are also increasing in situ temperature. Naturally, like, okay, say for example, okay, the energy requirement is going to go down. This is where you have the system. The moment you have the copper sulfide, okay, so nano objects, then you can actually start seeing that, okay, it's going to be active for the system, which is strengthening now, like say the copper oxide, which is a known combination. That's what in fact we have proposed. So that means like now these things are assisting through the plasmonic activation. So that's what you have. So then from this point, if you try to conclude, okay, neutral versus say for example basic medium, I think as you realize that, okay, so the catalysts, the electrodes which are stable under neutral conditions, okay, so which is over a longer period of time. That means like if you, I mean, just like to this, recently we started this one. So people mostly talk about, say, for example, these heterojunctions, but now that we have a good combination of, say, for example, the P-type materials also, you can actually try to look at like the recent materials which are like say oxyhalides, which are not very well explored. Okay, so on say for example, you try to take once again the recipe is like copper based PLP type material. We are going to retain that one, but only thing is like the 45% decrease in the activity you look at after 6-7 hours, because even though whatever I said it, whatever has been published, but finally there is a degradation of the, I mean the material. To prevent that, okay, this oxyhalide combination is something which we are working on right now. I think the observations will be, of course, will be communicated. So probably with this I stop, and okay, so these are the students who contributed. I think the boy who is say, standing here, I think he's the one who contributed to the work. And this is the girl, okay, so who is doing now this work, okay, so these are the students who contributed to this. So just like the take home message is like, okay, so this is a known reaction which I'm revisiting. There is nothing new in this, but only thing is this is not actually a practical approach for the very simple reason that it's very easy for me to say that, okay, water splitting is a green hydrogen, whatever. But as on today, it doesn't go the way we can think of, our students can think of. For that, okay, the only option you have is that identify good electrodes. And last 10 years, you see like there's plenty of work which is going on. There are champions in the world who are like Professor Domen in Japan. I think they are the champions who are working on it. Professor Yoda, these kind of people. But I think the understanding is that, okay, you need to have a good combination of the electrodes. You can do a full cell reaction, this limited one. So I stop here, and maybe I'll be happy. I didn't talk on plasma catalysis because in bits, I think 3-4 times I talk only about plasma catalysis. I thought that let me give a shock to Sonakrai. Okay, so that's how I changed the topic from one to another. I mean, I have also given the same abstract which I have talked. Okay, I stop here.
Long live India and France friendship.